Okay, so today we're going to finish up this whole first third of the course on quality control and quality assurance with some advanced statistical tool discussion. And we'll have a Kahoot at the end, kind of review, check on some of the basic knowledge on box plots and things like that. And this new plot called a dendogram, which you may or may not know about. And then we'll do a full review on Tuesday. So bring all your homeworks, your questions, and everything. We'll go over all of those. Make sure that you're finally tuned up for the test on Thursday. I want you guys to do well. So most of your grade is from the exams. So we want to make sure that each of those exams is good and that you have a good, strong performance the whole semester. Okay, don't dig yourself a hole here at the beginning and have to try and find your way out. All right, so that'll be great. All right, let's jump in. So we're going to talk about multivariable or multivariate statistics today. And so this is the application of statistics to data sets with more than one variable. And this is where we can incorporate some of the qualitative variables like color or texture or granularity. Of course, then you have the actual, the numerical data, size, weight, volume, those things, number of components, the identities of the components, which is categorical data. Concentrations, again, would be numerical, but origins would be categorical. So we've got a mixture of different data types. And a lot of the statistical tools require numerical values. And so sometimes, we can come in and we can still take origins and we can code them. Okay, so like let's say, for example, we have 3 different regions that we want to look and see what kind of dependency there is on the region. We can code, so region, we can numerically code them. We could say region -1, 0, and 1, and we can put those numbers into our statistical package, and it will be able to calculate, like an ANOVA, the slope related to region, and see if there's a significance or a p-value associated with region. So that's what we call coded values. But you could do that with color too, color 1, color 2, color 3, and you could then calculate the dependency, the slope on color, if there's a dependency or not. What's the p-value related to color difference? You could actually use those statistical tools. So that's what we mean by coded values. Now, we don't want to prejudice the numerical values because the regional value or the color may be one of the more discriminating factors. And so we want to take into account somehow these qualitative values too, because they are very important. And what this term is, this totality of circumstances, is what we're really looking for. So we're not just looking for a narrow view of a numerical data point. We're trying to look at the totality of the circumstances. So let's think about this. We were walking along and we see white powder on the ground. Is that scary or not?
Where are you at?
You said yes. Exactly. You said yes, and you asked, where are you at? Yeah. So what were you thinking in your mind?
Fentanyl.
Okay, fentanyl. Yeah, exactly. In a crime scene, you're like, I'm getting the gloves. But you asked, where are you at, right? Yeah, if you're at HEB, probably not, right? You're on the baking aisle. You're on the baking aisle, and you see a white powder, and then you look over there, and there's a flour sack that's leaking. The totality of circumstances. So that's what we're thinking of. Is this? What is the totality of the circumstance? If you're checking your mail and the white powder falls out. Yeah, wait a second. Yeah. So this is, again, a different circumstance, different response. So that's what we're looking for. Now, incoming evidence, this isn't in your notes, but it's a picture from the third edition, the book for the course. You see these different seizures, and you see that you can immediately sort of break it into groups or block this data. These groups here, look similar. This one looks unique. These green ones, there's a bunch of little green tablets. This one looks different, so we might pull that one out and circle these. So these are all probably one group. They have the same color or same appearance. A lot of times that initial screening is totally qualitative. It's how does it appear? What does it look like? Is there, not just color, but looking at the tablets, is there a roughness difference? Are these tablets shiny and those are dull? They may be the same color at a distance. You look closely, these are shiny, those are dull. That might be enough to discriminate between the two. So break them into those groups. You want to, again, the purpose of a forensic scientist is to separate and eventually individualize, right? So you want to classify and separate and discriminate between the different things. So most of the research done on the second floor in the forensic science area, so I'm on a lot of their committees, their doctoral committees or their master's capstone committees, and many of their studies are on discrimination analysis. Can we find a factor that will discriminate between these two different things? The most difficult one I saw was all of the black automotive carpets. So here's like 50 samples of fibers from black carpet and automobiles. How can we distinguish between them? And they were able to do that with UV Vis and a bunch of other tools and Raman. They were like, yeah, this is a Toyota, this is a Nissan, this is a Ford. But you look at them with your eye, it's just black carpet fibers. It's really very difficult to discriminate between those two. Over here, this was a lab seizure. These are, different steroid samples and so on. And so you could see the different types of bottles, some with different kinds of caps. And so this is how they broke up this grouping. You even have some odd ones out here, but once you have this group, you add them up, you take you pick 20 and then 10% of the rest, and then you have your sampling plan. So this is the data that we're going to have today. So this would be a large cocaine seizure that's labeled A, B, and C. So they went through the packages and they said, well, we can determine that there are 10 packs in each of these categories, in each of these groups. And we're going to label them A, B, and C. And the investigator's asking, is there any pattern or groups within these three seizures, or are they all the same? Or could they be related in some way, whether they're the same source? Maybe there's a sample prep thing that distinguishes between the two. So we'll spend the morning analyzing the data related to these three seizures. Since there's only 10 packs in each of the groups, we're going to analyze all 10. So we'll have all of the data on all 10, all 30 of these packages. Okay. All right. So when we run these through and collect the percentages, we find that there's three components in these, three main components that we're interested in. Cocaine, procaine, which is, again, a molecule similar to cocaine, and then caffeine. And sometimes they mix in caffeine to mask the missing ingredient. So they spread that cocaine away, over further packages by mixing in caffeine. It's cheaper and it can mask the missing stimulant of cocaine. And then here's the case ID. So, bag A, or group A, bag 1, 2, 3, 4, 5, 6, up through 10. And then group B, 1 through 10, and group C, 1 through 10. And so this is an important skill in statistics. It's called blocking the data. So the case ID column is split into two columns. So notice how if we leave A1 in the same little cell here, the software is going to treat it differently than it treats A2. It won't be able to group by A. So we need to go in and actually split this. Let's say somebody prepared this spreadsheet or this data set for us, and as an analyst, we're looking in this and we're saying, no, you got to split those two things apart. So we're going to actually have to split this case ID into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so that all of this whole group is blocked by group A. You see what I'm doing? I'm getting rid of those numbers so that all of that group is labeled A. So now the software knows that is a set of baggies A. There's 10 of them. If we combine those, then each one of those is an individual bag. And we're not trying to figure out if there's a difference between baggie number 2 in the A group and baggie number 3 in the A group. Okay, we're trying to see if group A is different than group B is different than group C. Okay, so that's what we call blocking data. Blocking is just another way of saying grouping. Okay, so statisticians will say block the data, and you're thinking, what does that mean? Well, it's not that you're stopping anything or whatever, you're just grouping the data. So that's what we did. So we split that column into 2 columns. So we have seizure A, so that the software can understand that those are all in a group together. And then we have individual packs 1 through 10. And then we start with group B, and then we have individual packs for group B 1 through 10. Okay. And so here's a scatter plot of all of the data. And this, I've been waiting for Excel to add this capability for, let's see, since 1992. When I started using Excel in graduate school, and I thought, man, I wish I could do a 3D scatter plot, and Excel has still never added it, you know. So it's just one of those irritations that I have with Excel. So you can go into Minitab and you can do a 3D scatter plot. And what conclusions can we make from this 3D scatter plot? So here on this axis we have cocaine, so it's going up in this direction. Procaine is going up in this direction. And caffeine, it's kind of cut off the page. I wanted to make the data panel as large as possible, so I cut off the caffeine. And so going up in this direction. So those little drop lines will help you know that this data point is really high in caffeine, and it comes down here and it hits this point for the cocaine here, and it hits this point for the procaine here. So if we were to draw this this thing, it would hit right there and it would come across. So that would be the number. It's about 6% caffeine. About 20% cocaine, and about, I don't know, close to 15% procaine. Does everybody see how the 3D scatter plot works? Okay, now just to let you know, how did I know how to draw this line right here? I'm going back towards the back, and it has to be parallel to this line and this line. You see, so I'm going back in a parallel manner to those lines so that I hit the back panel. And then when I hit that back panel, I mean, that's kind of a judgment call, but still, when I feel like I've hit that back panel, then I come across a parallel to this line and this line. So I'm coming straight across until I hit the 6. So that's just how to read those. Sometimes you have to draw some lines on there, or you can go actually find that data point in the data table, and you'll have all 3 values. But okay. Any questions on the 3D scatter plot? Can we draw any conclusions from this 3D scatter plot? I see a few shaking their head. Anybody that say yes? Okay, what can we draw?
Seizure A has the highest average concentration.
Seizure A, yeah, the black group is higher in cocaine than the other 2. So notice how the black data points are all clustered together, and there aren't any red or green ones mixed in. So this says A is unique compared to B and C. So B and C are all intermixed. So there is a separation between the groups. So we know A is different than B and C. We can't say much about B and C. They look overlapping and intermixed. So this is based on these concentrations of these 2 components. We have good separation. So I'm going to mark this. Good separation between A and BC. So that was easy to do. 3D scatter plot, look at it. Sometimes it jumps out at you, and this kind of jumps out. Let's say it didn't. Okay, we're going to look at a lot of different ways to analyze the same data. So looks like A is different than B and C. Okay, and there's a negative correlation between cocaine and procaine. So let's see if we can figure that one out. Okay, so if we're looking at this, if we look down at all of the data, we see that when caffeine or when cocaine is high, procaine is low. So see, all of this group is down here in this part of the procaine region. So the high cocaine region overlaps with the low procaine region, and vice versa. So when we're high in procaine, we're low in cocaine. So that's a correlation. But you may not have picked up on that in terms of the scatter plot, but over time, maybe you'll be able to pick that up. We're going to see that in other plots as well. So here's the box plot. So you can go to Minitab, do a box plot. This is with groups. We're using the cocaine, procaine, and caffeine, and we're gonna categorize it by seizure. So seizure A, B, and C. So you see these are the groups: Group A, Group B, Group C. Each of those has 3 components. So there's nine chunks of data. This is the concentration of cocaine in Group A, and Group B, and Group C. What conclusions can you make from here? Yeah, so this is nice that you're looking at the y-axis and you can see that in terms of the data that the cocaine is higher here. If you could draw a line between the bottom of this box and it goes above the tops of the other boxes, then you know it's different. In fact, we're comparing it really to the cocaine one, cocaine compared to cocaine, and you see there's a huge separation between those boxes. If the boxes overlap, let's look at caffeine. So you see here caffeine for all of these, those boxes overlap. So there's probably not a statistically significant difference between the caffeine in all 3 samples. Because for a statistically significant difference, the boxes should not overlap. Okay, there's some other things we can draw from this. Can we see that correlation that we found in the other one?
Very close to identical.
Yeah, that's right. B and C, look, they have the same pattern. You can kind of see this pattern here. So they're listed in the same order. So you see that same pattern for those 2, and you see a different pattern for A. So you can look at patterns within the groups using box plots. And okay, and then you can kind of see the let's see. You can kind of see the correlation here. So notice that cocaine was here and here, and when cocaine went up, in terms of A, right? When it went up, then the procaine went down. So you have this pattern and it's broken in A. Well, what happened? Cocaine went up and procaine went down, and caffeine stayed pretty much the same. So whether that's a significant correlation or not, we don't know yet, but we know that there's some connection between procaine and cocaine. This is a correlation plot, a matrix plot of correlations. This is one of the busier plots that would confuse the heck out of whoever you showed it to, okay, like I'm doing to you right now, okay. And so what it does is it takes every variable and plots it by every other variable. So that's pretty cool. If you had a whole bunch of data and you thought, let me just look to see if there's any variable that separates the data, you'll be able to find it on here. And it's real easy to do because you just tell Minitab, say, well, I'll plot, like you have 5, let's say I have 5 different compounds with different compositions. Then this would be a 25 panel plot. It'd be 5 different groups of data, everyone plotted by everyone else. Okay. Now the diagonals are always, straight lines because this is cocaine plotted versus cocaine. But notice how you have complete separation. So cocaine alone is enough to identify A is different than B and C. So this is A and this is B and C. So just on the cocaine value alone, I get complete separation between the data. Okay. Notice on the procaine, I get somewhat of a separation, but they overlap right here. So this is B and B and C, and this is A. They overlap, and here they're intermixed. So this is For caffeine, there's really no significant difference between the three groups. Now, this is a correlation, a matrix plot of correlations. And so how do we see the correlations? Whenever you get separation of the groups and they give you a slope, so like right here, you have B and C and A. So this is saying that cocaine and procaine are negatively correlated. Does everybody understand the negatively part? When one goes up, the other goes down. It's a negative slope in this plot. Okay. And let's look at the other one. If we plotted procaine versus cocaine, we still get that negative slot. So these are going to be the mirror images of each other. And so we get a negative correlation for both of these. So I would just say same. It's just one is Y and the other is X, and on the other side we flop the X and the Y. So this is procaine plotted versus cocaine. Okay, anything else? I'm not sure I can pull anything else out of this. We get good separation here between cocaine and caffeine, but there's really the slope is 0, right? So even though we have good separation, it's really the cocaine that's given us the separation. And we don't have a correlation. The slope is 0. If the slope was positive, we'd have a positive correlation. If it was negative, we'd have a negative correlation. If it's 0, we have no correlation. So, yeah. Yeah, I'm not really seeing it. Okay, so I think that we've pulled everything we can out of this plot. Any questions on this one? Now, you might say, well, this is a really strong correlation. Well, then naturally, because it's cocaine plotted versus cocaine. So if cocaine goes up, cocaine goes up. If it goes down, it goes down. But, so those are trivial correlations. But this was nice that we could say, yeah, we have complete separation between group A and group B and C. Okay. So now let's look at the display the p-value. So we did the correlation matrix, and so we're going to look at the p-values of those correlations. So we need to know the null hypothesis. Anytime you use a p-value, you want to know what the null hypothesis is. So our null hypothesis for a correlation analysis is that there's no correlation. And so the p-value is the probability that that is true. And this is the results, the Pearson correlation, which is the R value. So you can go up here and do correlation, put in your 3 data points, and say display p-values. And so here's the table that we get in the session log. So you go to the session log and you see this correlation analysis. We have every variable compared to every other variable. And so it's a triangular matrix. If you want to look back at the plot, it's like these three plots right here. All right, so it's that bottom triangle. But instead of a plot, it's the numbers. So it's the slope of that data, that scattered data, and the p-value. Okay, so we saw that cocaine and procaine were negatively correlated. You see that negative sign. So that's good. And here's our p-value. Hey, that's fantastic. 0.003. We know there's a strong correlation there, or statistically significant correlation. The magnitude of this number would be how strong it is. So this number tells you how strong the correlation is. And this tells you the statistical significance. And the confidence is 1 minus p, or 99.7%. So we're 99.7% confident that we have a negative correlation between these two components. Let's look at procaine and caffeine. So this number right here, we see a weak correlation, 0.04. That's a small number, so it's a weak correlation. It's negative, but is it statistically significant?
No.
Yeah, correct. No, it's not. So there's a 83.5% chance that that's zero. So the only reason it's non-zero is statistical uncertainty. Okay. So that number, that weak correlation, you can't depend on. There's an 83% chance that it's actually zero. What's your confidence? 1 minus that. So, 17% confident. Okay, 16.5% confident in that 0.04. Okay. But this one, notice how when we were looking at the plots, cocaine and caffeine, let's see, where's cocaine and caffeine? Okay, it's this one here. This plot, I said, well, that has a slope of 0. It's not quite 0. It's slightly positive because of these numbers up here. Okay, so that's a slight positive correlation. Looking at this plot, I can't tell if it's statistically significant. Okay, but I do the numerical analysis and I get the table out where I got the p-values, and now I can say that it is. This is the p-value of that correlation, 0.005, and that's less than 0.05. So this one is statistically significant and positive. So there's a positive correlation between cocaine and caffeine. Numerically, it's 0.5, and then the p-value is 0.005. So I'm 99.5% confident that that's a real correlation. So this is where the numerical p-value really comes in handy. Looking at the plot, you can get a feel for the larger features, the more, the strongest features. But even the weak features, we need to get in and actually look at the numbers and calculate the p-values. Okay, so we kind of see that when cocaine goes down, cocaine goes up. That's the negative correlation. And then they have this little weak this weak correlation that when cocaine goes down, this number went down a little bit. So that's what these little arrows are. So it's saying that these guys, when compared to cocaine, go in the same direction as cocaine, but slightly. Okay, now let's say that our data. Let me try to. This dendogram or clustering analysis is really useful when you can't see patterns in the data. We've already seen patterns in the data. So, but you always kind of, let's sort of erase that from our mind. Let's come at this data and say, I've got so many different bags and so much different information. I've got 3 different concentrations, and I can't, in the scatter plots or anything like that, determine anything unique about A or B or C. So this would be a sort of a data exploratory method where you start looking at your data. This will work with any number of variables. So you could have 50 different variables, which will be a case when, this might pull out a pattern that you couldn't see otherwise. It's called clustering. And so this is how it works. It produces this diagram called a dendrogram. And dendritic growth or dendrites, they branch a lot. And so this is why this is called a dendrogram, because it's a branching diagram. Now, the way we produce it is like, here's our data, and it's just plotted in terms of 2 axes, X and Y. And so we look at the data points and we calculate the distance between every data point. So this is something, you take the distance from 1 to 2 and 1 to 3 and 1 to 4 and 1 to 5. So you've got the distance of 1 to all the other data points. And then you go to number 2. Well, we've already calculated the distance between 2 and 1. So we just calculate 2 to 3, 2 to 4, 2 to 5. And so the next column is 1 spot smaller, 1 spot shorter. And then we go to 3 and we calculate 3 to 4 and 3 to 5. And then we go to 4 and calculate the distance from 4 to 5. So we see we produce this triangular matrix. And then we look for the smallest distance in that triangular matrix. Those are the 2 closest data points. So looking at that, we would see that 2 and 3 are the closest. So we would combine them. Okay. So that distance is plotted here on this linkage distance. So that's this top bar. That's the distance between 2 and 3. And so we combine 2 and 3. And how do we do that? Well, we calculate the average X value and the average Y value. So that puts a data point midway between 2 and 3. So there's a new data point right there. And then we redo the clustering analysis. So we look at the distance between this 2-3 combination and point number 1, the 2-3 combination in 4, 2-3 combination in 5, and then we go to point number 1 and calculate 4 and 5, and then we go to 4 and calculate the distance to 5. And so can you see what the next grouping will be? It'll be combining 2, 3, and 1. So we group that. So this is why this is called clustering. We start at the closest cluster and we get bigger and bigger and bigger until we have the whole data in one cluster. So now there wasn't much more difference or much more distance between 2 and 3 and 1. So when we cluster those, we calculate their average values, and now we're right there in the middle. And then we draw that linkage distance between 1 and the cluster 2, 3. And so that's where this horizontal bar comes. So we can see that 1 was very close to cluster 2, 3. Okay, and then we do this analysis, the distances again. And what's the next thing to combine? 4 and what?
5.
Yeah, 4 and 5. So we next cluster 4 and 5. And that's this distance right here. So this is the distance between 4 and 5. And that's how we plot that bar. So 4 and 5 is combined. They're this far away from each other. So we can see just from this plot, 2, 3 were the closest. And 1 was close to that group, but 4, 5 were their own group. So you can find groups in the data. Now, this is really easy to see in 2 dimensions, right? I can see that this is group 1, that's group 2. But like I said, a dendrogram will work in n dimensions. You could have 100 different dimensions, and this will put them all on a 2D plot and tell you which groups are most similar. And it'll allow you to determine how many groups in the data that you have. So if you didn't have any difference in color, didn't have any difference in roughness, size, any of these characteristics that would allow you to separate your samples, and you do your sampling plan, you calculate 20 and 10% of the remaining, and you do that, and then you look at your data, you got a chromatograph with all of these different peaks, and you analyze all of them, you got 20 different compounds. The dendrogram will allow you to find patterns in those compounds. And if all of them are pretty close, you say, well, even though I can do the dendrogram, they're all pretty close to the same values. I probably have, they're probably the same. Like this seizure probably has all the same characteristics. But if you get 2 groups that are far apart like this, 4 and 5 may be different than 1, 2, and 3. You say, well, maybe I have inside this group, to me, that looks the same. This group is homogeneous. I may have 2 different groups, actually. And so then you could analyze a few more and see if they naturally fall into that pattern of 2 groups. So dendrogram is pretty nice. It always ends in one big happy family. Okay, and this will tell you how far you had to go to get those groups to combine. So this would be the distance between that cluster and that cluster right there. So if it's really tall, then these groups are really different. And if it's not very tall, they're not very different. Okay. So this is the dendrogram for our data, for the A, B, and C groups. So you can look at this and I can ask you a question, that's cluster 1. So what does that tell us about B6 and C8? The what? Yeah, they have almost the same concentration of all 3 components. Because this is the difference between cocaine squared, the difference between procaine squared, and the difference of caffeine squared. All added together, take the square root, that's the distance. So if any one of those differences is big, they're going to be far apart. But if those differences are similar, the square differences added together, take the square root, that's going to be a very small number because you have lots of things that are close to 0. You got 15 minus 16 squared and 12 minus 11 squared and 0.5 minus 0.4 squared. Those are all really small numbers. Square them, add them, take the square root. That's the Euclidean distance. And so this tells us B6 and C8 are almost identical. Okay. What is there any data point that's an outlier or wonky and doesn't fit into anything? Maybe you can't see that. Which one? B1. Look at this guy right here. He is odd. It doesn't join any group until like the last minute. So it's B1, you know, he's sitting off in the corner, you know, looking around, not doing anything. So what other observations do you see? So like the next one is like B8 and C6. The next one is B2 and B7. Then C2 joins in. So I'm just kind of working my way up, you know, and I have all of those combined. And then here's C4 and B9. Notice I'm saying C and B, B and C, B and B. All of these are intermixed. So can we determine from this dendrogram that B and C are a group and they don't join anything in the A group until the very end? So the last grouping brings in A. So this is B and C all mixed together. This is A. They finally join in, and we have an outlier. Okay, so we've got a really unique sample at B1. But if you were to look at this dendrogram, you would say, well, we really have two groups. We have this huge cluster right here, and then we have this huge cluster right here. It's, I don't know. I mean, if you don't know how to interpret it, the diagram looks crazy, right? But think of how useful this is. If you had a chromatogram with 20 peaks, you could use this to find, you know, data clusters. Yes. Yeah, so A1 is unique as well. So yeah, that's good. Also curious. Yeah. Now I would say I've been saying outlier, so let me maybe back off. Maybe I will back off on this one. I'll say curious. Why am I starting to like get nervous about using the word outlier?
Because you don't know if it's statistically significant.
Yeah, and we've already done some tests on that, haven't we? The box plots. So if B1 was an outlier, it would have shown up as an outlier. You know, that is the statistical test for that. So maybe I should just say that's a curious sample instead of definitely an outlier. Okay, so then we get to principal component analysis. So this is one of the goals of principal component analysis is to reduce the number of variables. So this was pretty easy because we had 3 variables and we could plot 3 variables on a scatter plot. But if we had a 4th variable, we'd be out of luck. There'd be no way to plot a 4th variable. We could use the dendrogram with 4 variables. We could use box plots and grouping with 4, 5, 6. It doesn't matter how many variables. It just gets confusing when you have 20 box plots, right? And so then you might use the dendrogram to pick 2 groups and then relabel those. So we relabel B and C group as group 1 and A as group 2, and then we could do box plots with those new categories. But principal component analysis looks at the data, and the goal is to reduce the number of variables. So variable reduction, you can write that down as principal component analysis. That's goal number 1, is to reduce the number of variables. So we can also say reduces the data space. So in our situation, we have a 3-dimensional data space. We have 3 components that we have numerical data for. And we would like to reduce it to 2 so we could easily plot it on a flat graph, you know. The second goal, so this is, I guess this is the first goal here. So the first goal of PCA is to reduce the number of variables to a plottable number. Okay. Second goal is to spread the data out. So, let's say this scatter plot wasn't conclusive and we had all of the data points on top of each other. There may be a way to do linear combinations of these three variables to where the data would spread out. And we would see a group on the right and a group on the left. So that's what we're looking to do. We're looking to find another way to plot the data to spread the data out. Okay, so this is how you do it in Minitab. And we're saying number of factors to extract. So we're going to try to extract 2 factors from these 3 variables. So how does it do that? Well, I mean, it's a big mess in terms of math, okay, and linear algebra. But it will take an equation, and we'll see that equation of a percentage of the cocaine number, a percentage of the procaine number, and a percentage of the caffeine number. So it'll create essentially 2 new axes that go through the data. It might, instead of these 3 planes here that we have, like these 3, you see the 3 planes, the white boxes. What if we drew a plane diagonally right here, like this? What's the mathematical equation for this new x-axis and this new y-axis? That's what principal component analysis is calculating. So it's trying to find a plane through the data where the new x-axis and the new y-axis are some kind of combination of the other axes. And then it'll plot the data on that new plane. Okay. So here's the components. You see factor 1 and factor 2. This might be like x and y. And you see x is 92% cocaine. It's flipping the sign on the procaine value, 68%, and 67% or 66% of the caffeine. So it's a linear combination of these 3 variables. And then the y-axis is almost using none of the cocaine. It's 68% of the procaine and 71% of the caffeine. So you see, that's just a linear combination of those 3 variables. And now we have 2 variables. We have an x and a y. And then we can plot that. And now this one is capturing 58% of the variability with this factor and 32% of the variability with this factor. That's what you get with this unrotated one. If you can rotate the plane and calculate another one so that you balance these percent variables, you see now with the rotated principal component analysis, we get a more even split. We get like 45% of the variability captured by factor 1 and 44% captured by factor 2. So these are 2 options for the principal component analysis. This is capturing 90% of the scatter of the data. So that's like an R value, R squared value, 0.9. That's pretty good. Yeah. And so here's the plot that we get. So that first factor, again, is that, what I was saying, the x-axis, and the second factor is the y-axis. And now we have a 2-dimensional plot. So we reduced the data space. We used to have a 3-dimensional plot. Now we have a 2-dimensional plot. And the goal is reached. We've separated the data. You can see that, there's no overlap between the data points. And so this is principal component analysis. Now, that's as far as I'm going to go with this, because I've not done a lot of principal component analysis, but I did want to introduce you to it with the 2 goals in mind. One is to reduce the data space, and the other is to increase the separation of the data. Okay. So, all right, well, let's take a Kahoot. We can review some things here. There we go. There's the game code. Oh, why the volume's not working? I like the song. It's gonna blow your ears out, I'm sure. No? Okay, it's on my laptop. It's a bop. I learned that phrase from that funny girl that plays ukulele, Elise or something. I forget her name. You know who I'm talking about? YouTuber. It's just funny. She did a little song on her hate comments. It was so funny. She's very talented in writing songs, writing lyrics. Is this everybody? Raise your hand if you need a few more seconds. Okay. All right. Great. Yeah. All right. Let's jump in. Ready? Set? Okay. Here we go. Oops. Get your thumbs ready. Yeah, look at that. You guys are on it. It's always best when I make the Kahoot the morning of, because then I really tell you in the lecture, you know, what's coming. What are ways you could group the folks in that picture? Right? Let's see. Where's my? It's just show media. There it is. You know, hair. You could do male, female. You could do various racial categories. You could do hair color, whatever. You know. So there's lots of ways to block the data. What's that? Okay. All right. I know it's fastest. Yeah. Okay. Cocaine in A is significantly different than cocaine in B and C. How do you know this? Okay, let me snooze this alert. Do y'all see that? No, you don't. Okay, very good. I'm getting notifications on my laptop about a meeting that I can't go to. All right. The line in the middle, this is tricky. The line in the middle of each gray box in this box plot is the blank of the data. 50-50. You see it? Oh my gosh.
Oh, wow.
I'm taking a picture.
We're all flipping
That's
coins.
right. All right. Y'all smile. This is great. Okay. That's great. Flip that coin, man. That is. It's the median. Yeah. So that's right. That's really great. Yeah. Second, I gotta snooze this notification. It's driving me crazy. Okay. All right, we have some swaps around now. Okay, the gray boxes in this box plot contain the blank of that group. So this is a word. I normally only take pictures and there's 100%, like everybody gets it right. I can take a panoramic of the class and y'all are wow, big spread on that. So this is that word, interquartile range, or inner quartile range. So you have 4 quartiles in the data, and the middle 2 are captured by the box. So from 25% of the data to 50 and 50% to 75%. So the box captures the 2 middle quartiles from 25 to 75. So 50% of the data is inside that box. Right in the middle is the mean. The line is the median. So you can see how the mean is the middle of that box. The median is offset sometimes depending upon the way the data spreads. What's the probability that there is a correlation between procaine and caffeine? Probability that there is. It's kind of a small, can you see? Between procaine and caffeine. So here's procaine over here and caffeine over here. So it's this group of data right here. Probability that there is a correlation. You're very thoughtful, coming in slowly. That's good. Yeah. So the p-value was 83.5%, which is the probability that there's no correlation. So the probability that there is a correlation is 16.5. Okay. What does the negative correlation between cocaine and procaine mean? I can make that bigger. Ooh, that did the opposite. So there's a negative correlation between cocaine and procaine. What does that mean? This is a multiple select too, so you could select 2 answers. Done a few of these. This one always makes me think we're down in the little tunes on Mario, you know, da-da-da-da-da-da. All right, the last person's just sitting there. We got time. All right. Okay. Yeah. Good job. So it's the up and down thing, right? When it's a negative correlation, one goes up, the other goes down, and vice versa. Don't forget the vice versa. Okay. All right. Multiple select. How many clusters are present in this dendrogram? Oh, can you see it? It's kind of tough to see. So you can look at these little areas here and see how many clusters you think there are. And this one would be a judgment call. We might have to arm wrestle over it. So that's why I let you have 2 answers. Pick your favorite. A couple of the answers are clearly wrong, but the other 2, yeah. So you might be able to argue that there's 3. So the argument for 3 is that these join up here, and then they join with this one way up here. So this would be the 3, the red, the yellow, and the blue. But it could also be 4. This would be a small group right here and a small group right there. So again, you might convince me there's 4 groups, maybe 3, but there's certainly more than 2 and more than 1. So the dendrogram, that's the downside of it, is that there's some subjectivity to it. You know, so you have to look at that data and say, well, I see 4. Okay, this is the last one. Yep, number 8. The purpose of principal component analysis, purposes, that tells you there's more than one. This one's easy. That's right. No, we're talking about the purposes, not the results, right? That's right. Yeah, that's right. All right. All right, we gotta have the little. All right, good job. Yay. All right, good job, Tyler. Very good. And runners up, Kaylee and Andrew. Good job. All right, well, you'll have a great time. We'll see you on Tuesday with the review. Update your data. Yes, Elise. Go to Kahoot and look for CHEM_prof. That's my handle on Kahoot, and you'll see all of my Kahoots. And then you could search maybe 4380, and that ought to bring them all up too. And you'll see all of the ones that are on there. Now, sometimes the L numbers don't line up because I'll move this lectures forwards or backwards a spot, but they're close. So all the like L8 and below, those would be in this section. All right. Yeah. I like making them, but I just need to make some more. Y'all can make them for each other. Yeah, so it's fun. Okay.